An international team of researchers has achieved a milestone that seemed unattainable: to manufacture a two-dimensional quantum material whose existence had been foreseen only in theory. This material is a crystalline topological insulator in the form of a thin atomic layer, constructed from tin telluride (SNTE) and capable of driving electricity exclusively along its edges. If you like this type of content, do not forget to subscribe to the channel and like the video. The particularity of these materials is that their interior remains insulated, while their edges behave like conductor cables. This property has enormous potential for future applications in high-efficiency electronics and quantum computing. The finding puts an end to more than 10 years of frustrated attempts to find a practical way to manufacture these two-dimensional systems, known as TCIs, topological crystalline insulators. The study, published in Nature Communications, has been led by researchers from the University of Jyväskylä and Aalto University in Finland. Through molecular growth techniques and low-temperature tunnel microscopy, the team has shown that it is possible to stabilize these quantum states in real and controllable conditions. This advance could revolutionize the way we understand and use modern electronics. A crystalline topological insulator, TCI, is a material that, although electrically insulating inside, allows the flow of electrons at its edges. This phenomenon is protected by symmetries of the crystal, such as reflection symmetry or mirror symmetrics, which makes it different from other materials. The key is in a property called Chern number with mirror symmetry. When this number is different from 0, conductive states appear at the edges of the glass. In the case of the SNTE, it was identified that this number reaches a value of plus or minus 2 under compression, guaranteeing the existence of two pairs of electronic states. This behavior is not only fascinating from a fundamental point of view, but also valuable for future technologies. Electrons circulating through these channels do not suffer dispersal or generate heat, which could lead to more efficient and faster electronic devices. The great challenge in performing a two-dimensional CRT has been to find a manufacturing method that maintains the necessary symmetry. In this case, researchers grew a two-layer film of SNTE on a substrate of niobium diselenium, NBSE2, using a technique known as epitaxis by molecular beams. Thanks to this process, they managed to keep the upper layers of the SNTE compressed, generating a biaxial tension that induces topological behavior. Experimental data clearly showed the existence of two peaks in the density of states at the edges of the material, a sign that the topological states were active. One of the keys to the study is the use of mechanical tension to activate the topological properties of the material. The SNTE in its natural form is not a TCI in 2 dimensions, but by applying compression, the system's electronic structure is modified, leading to a voltage-induced topological phase transition. To confirm that the material created was actually a TCI, scientists carried out several experiments. The most direct test was the observation of peaks in the state density spectrum, located at the edges of the material, indicating the presence of expected conductive channels. Although this discovery is still in the experimental phase, its implications are very broad. The fact that the material works in conditions close to ambient temperature makes it a promising candidate for next-generation technologies.